Hi friends, welcome back to my YouTube channel. So today I am going to discuss about error control. So previously we have discussed about flow control, and now we are going to discuss about error control from error correction and error detection. So here the mostly the topics covered in this video is related to KTU syllabus from computer communication EC 407. So this topic is from module 2, and let's go to the video. Let's start the class. So this is a part 1. I'm going to discuss part 2 and part 3 and part 4, part 5 are there. So it's a huge topic, but you can refer this video when your exam when your exam comes, and you can refer this, and this will help you so much. So yeah, let's go to the video. So we have discussed flow controller, like the protocols that are used in flow controller, that symbol protocol and stop and wait protocol, and everything we have discussed. So now we are discussing about error control. So error control, the first topic is error correction. So as we said before, error correction is much more difficult than error detection. So error correction is difficult than error detection. So in error detection, the receiver needs to know only that the received code word is invalid. In error correction, the receiver needs to find or guess the word or the code word, that is original code word, that is same. So that's why the error correction is much more difficult than error detection. So what they're trying to say is the error detection is much more difficult. Sorry, the error detection is much more simple because they only need to verify the data that is sent invalid or valid. So that's it. But error correction means they need to get the data, the correct original code word that is sent. So that is a huge task for error detection. So we can say that we need more redundant bits for error correction than for error detection. So in another way we can say that in error detection it needs lesser redundant bits, and in error correction it needs more redundant bits. So figure shows the role of block coding in error correction. So we can see that the idea is the same as error detection, but the checker function are much more complex. So if you go for the error detection, we will discuss next. So in the as much as this is the same format, error detection and error correction have the same block, same figure. So there is only a difference in the block coding, error correction. In the only the difference is in the checker function. So sender and receiver is there. Sender is this and receiver is this. So we have k bits data word, and there is a generator function is there, and n bit code word will be generated, and this will transmit it to the receiver, and there is a decoder, and there is a code word will be sent to the receiver side, that will be the n bits, and there is a checker function. So checker function will check it is correct or not, and it will provide the data word. So this is happening in the error correction part. So we'll, for example, so we can discuss this in an example, with an example. So this is the table 2 we are seeing here. So for each data word 00011011, there is a code word related to that data word. So let us add more redundant bits to previous example to see if the receiver can correct an error without knowing what was actually sent. So we add 3 redundant bits to 2-bit data word to make 5-bit code words. So what we are doing, so code word is 5-bit and data word is 2-bit. So what we are doing, we are adding 3 more redundant bits. So that means it will make 5-bit code, 5-bit data word that is similar to code word. So we are adding 3 more redundant bits to the data word, and it will make 5-bit code words. So table shows the data word and code word. Assume the data word is 01. Assume the data word is 01. So assume that we can assume that the data word is 01. That means this one, the 01, and the sender the sender consult the table, use an algorithm to create the code word 01011. So when the data word is 01, it will create a code word of 01011. So this is the code word. So the code word is corrupted by transmission. During transmission, and 01001 is received. So error in the second bit from the right. So here you can see the code word is generated from the data word 01 is 01011. So the second last bit of the code word is corrupted here. So during the transmission, the code word is changed to 01001. So first the receiver finds that the received code word is not in the table. So this means an error has occurred. So detection must come before correction. So detection is done before the error correction. So the receiver, assuming that there is only one bit corrected, uses the following strategy to guess the data word. So already we know that the data word and code word combinations. So once the code word is, the data word is 01, the code word is 01011, but we got a corrupted code word is 01011. So the second last bit of the code word is corrupted. So we can make a guess that only one bit is corrupted. So we need to guess the correct data word. So that's why we need to do this. These steps are in the following steps we can do. So comparing the received code word with the first code word in the table, such as 01001 versus 000. So the receiver decides that the first code word is not the one that was sent because there was two different bits. So that is the one case, because you see 01001 is related to data word 00, and the code word is 0000 is the code word for data word 00. So here you can see only two bits are changed. So in our case only one bit is corrected. So by the same reasoning, the original code word cannot be the third and the fourth in the table. So third and fourth, if you see, there are two bits are changed. Two bits are corrupted comparing to the our original one. So we can say that the third and fourth one are not related to this corrupted one. So the original code word must be the second one in the table, because it is the only one that differ the received code word by one bit. So the receiver replaces 01001 with 01011 and consults the table to find the data word 01. So this is the process that we are using to check the correct to detect the correct code word. So I hope you understood the theory or the process. So we can go to the next section. So Hamming distance. Hamming distance is the one of the central concept in coding for error control is the idea of the Hamming distance. So one of the central concept in coding for error control is the idea of Hamming distance. So Hamming distance between two words of the same size is a number of difference between the corresponding bits. So we show the Hamming distance between two words x and y is d of x comma y. So the Hamming distance can be easily found if we apply the XOR operation on the two words and the count the number of ones in the result. So Hamming distance can be easily found out by using XOR operations in the two words and count the number of ones in the result. So note that the Hamming distance is a value greater than 0. So that's why we can say that Hamming distance between two words is a number of difference between the corresponding bits. So for example, so let us find the Hamming distance between two pair of words. So Hamming distance between d of 000, comma 011 is 2, because 000 XOR 001 is 011. That means there are two ones. So that we can say that the Hamming distance is 01. So I hope you know the XOR function. XOR function means 00 will be 1 and 11 will be So if the two bits are same, then the result will be 0. If the two bits are different, then the result will be 1. So that is the case. So if you add XOR these two, so if you go for 0 0, then the result will be 0. And if you go for 0 1, the result will be 1. If you go for 0 1, it will be 1. So it is XOR means addition. Addition, one of the addition. So you can if you can refer that. I will be discussing this in after this, so you will get an idea after that. So I hope you already know this XOR function. So and also we can, the second example is d of function Hamming distance d of 10101 comma 11110 is 3, because XORing these two data words, we will get 3 ones in the answer. So we can say the Hamming distance is 3. So what we are doing, 1 1 1 plus 1 will be 0, and 0 plus 1 will be 1, and 1 plus 1 will be again 0, and 0 plus 1 will be 1, and 1 plus 0 will be 1. So the resultant will have the 3 ones. So the maximum Hamming distance is 3. So minimum Hamming distance. So although the concept of Hamming distance is the central point of dealing with error correction and error detection, the measurement that is used for designing a code is the minimum Hamming distance. So in a set of words, the minimum Hamming distance is the smallest Hamming distance between all possible pairs. So it is the minimum Hamming distance between all the possible pairs. So we use dmin to define minimum Hamming distance in a coding scheme. To find the value, we find the Hamming distance between all words and select the smaller ones. So we have an example, two examples to discuss more on this. So find the minimum Hamming distance of the coding scheme. Table is here. So the solution is like we have already provided the solution, so we can go for first find the Hamming distances. So d of 0 0 comma 0 0 0 1 equal to 2. We need to XOR these two code words, then we will get 2 ones over there. And we need to do the same process, 0 0 0 comma 1 0 1. So there also we will get the resultant will be 1, then 0, then 1. So there are also 2 ones are there. So everything have the 2 is the Hamming distance. So the minimum Hamming distance will be 2. So in the second option, second example, if you see here, so we have 4 ones and 3 ones are there. So in that we need to take the minimum Hamming distance as 3. So this is the case. So next thing is 3 parameters. So before we continue our discussion, we need to mention that any coding scheme needs to have at least 3 parameters. So any coding scheme have at least 3 parameters: the code word size n and data word size k, and the minimum Hamming distance will be dmin. So a coding scheme C is written as C of n comma k with a separate expression for min. So for example, if we can call our first coding scheme comma 3 comma 2, so dmin equal to 2, and the second coding scheme C of 5 comma 2 and the dmin is 3. So in this way we can represent a coding scheme. So Hamming distance and error. So before we explore the criteria for error detection or correction, let us discuss the relationship between the Hamming distance and error occurring during transmission. So when a code word is corrupted during transmission, the Hamming distance between the sent and the received code word is the number of bits affected by the error. So it is the number of bits affected by the error. So in the other words, the Hamming distance between the received code word and sent code word is the number of bits that are corrupted during transmission. For example, if the code word is 0000 is the sent and 01101 is received, so 3 bits are in error. since the send code word is 00, so there is a 3 bits are changed in the received one. So and the Hamming distance between the two is d of 0000 comma 01101 equal to 3. So there are 3 bits of errors in the received bits. So minimum distance for error detection is, so now let us find the minimum Hamming distance between the code if we want to able to detect up to S errors. So if S errors occur during transmission, the Hamming distance between the send code word and the received code word is S. So let's talk about that. So now the minimum Hamming distance in a code, if we want to able to detect up to S errors, if S errors occur during transmission, the Hamming distance between the send code word and the received code word is S. So that is already we have discussed. So just in the words we can describe like this. So if our code word is detect up to S errors, and the minimum distance between the valid code must be S plus 1, so that the received code word does not match the valid code word. So that is the thing. So the valid code word does not match with the received code word. That means the received code word must be S plus 1. So in other words, if the minimum distance between all valid code word is S plus 1, or the valid code word S plus 1, then the received code word cannot be erroneously mistaken for another code word. The distance are not enough S plus 1 for the receiver to accept as valid. So the error will be detected. So we need to clarify a point here. Although a code with a daemon equal to S plus 1 may be able to detect more than S errors in some special cases. So only S or fewer errors are guaranteed to be detected. So to guarantee the detection of S errors in all the cases, the minimum Hamming distance in the block code must be dmin plus S plus 1. So this is the criteria. The minimum Hamming distance in a block code must be dmin equal to S plus 1. So for example, the minimum Hamming distance between for the first table, so that you remember the first example we shown there. So in that table is 2. The minimum Hamming distance is 2. So this code guarantees detection of only one single error. And for example, if the third code word 101 is sent and one error occurs, the received code word does not match any valid code word. So if any error occur, however, the received code word may match the valid code word and the error are not detected. So for example, our second block code scheme, that is table 2, has dmin equal to 3, and the code can detect up to 2 errors. Again, we can see that when any of the valid code word is sent, 2 errors can create a code word which is not in the table of valid code words. So the receiver cannot be fooled. However, some combinations of 3 errors change a valid code word to another valid code word, and the receiver accepts the received code word and the errors are undetected. So we can look up this geometrically. Let us assume that the same code word are R and is the center of the circle with the radius S. So all the received code words that are created by 1 to S errors are points inside the circle of the perimeter of the circle. So all the valid code words must be outside the circle as shown in figure. The geometric concept of finding daemon in error detection. So the figure shows the diagram. So the square shows the any valid code word and dots represent any corrupted code word within S to S errors. So minimum distance for error correction. So error correction is the complex than error detection, and when a received code word is not a valid code word, the receiver needs to decide the valid code word was actually sent. The decision is based on the concept of territory, an exclusive area surrounding the code word. So each varied code word has its own territory. We use geometric approach to define the territory. So we assume that each varied code word has circular territory with a radius of t and the varied code word at the center. So for example, suppose a code word x is corrupted by t bits or less, then this is corrupted code word is located either inside or on the perimeter of the circle. So if the receiver receives a code word that belongs to the territory, it decides that the original code word is one at the center. So note that we assume that only up to t errors have occurred, so otherwise the decision will be wrong. So figure shows a geometric representation. Some text use a sphere to show the distance between all the varied code blocks. So for example, a code scheme has a Hamming distance d min equal to 4. What is the error detection and correction capability of the scheme? Solution: the code guarantees the detection up to 3 errors because d min is 4, but it can detect the 3 errors and it can corrupt up to 1 error. So in other words, if the code uses the error correction, part of its capability is wasted. So error correction codes needs to have an odd number of distance, odd minimum distance 3, 5, 7. So it is showing like this. So territory x and territory y, the center x square is the valid code word and d min greater than 2t, and since the next integer increment is 1, we can say that d min equal to 2t plus 1. That's why we are saying the Hamming distance should be odd numbers 3, 7, 3, 5, 7 like that. So that is all about this one. So we have discussed error detection, error correction, and basics of error correction and error detection, and mostly we covered the part of error correction. So error correction is much more difficult than error detection. So and also we have discussed about Hamming distance. So that's the thing, and we have already discussed some examples here related to XOR addition, and also the Hamming distance and the error, and the minimum Hamming distance for error detection and error correction. So we discussed both minimum distance for error correction and error detection. So if you have any doubt, please feel free to comment in the video and ask me if you have any doubt. So if you like this video, please subscribe my channel, and thank you. See you in the next video with the remaining part. So we tomorrow, I think next section we will discuss about error error detection. So see you in the next section. Thank you.